My name is Qingzhao. I'm a professor in data science and biostatistics at Louisiana State University. It's my honor to introduce our two speakers today. Dr. Alan Paul is associate professor at Louisiana State University Health Science Center, specializing in big data analytics, AI, and machine learning. Recognized among the top 2% of scientists worldwide by Stanford University and elsewhere publisher. His work focuses on resilient and robust intelligence. As an IEEE senior member, he has also served as an editor for several prestigious journals and held key roles in academic conferences. Dr. An-Chao Tsai is an associate professor at National Pingtung University, Taiwan. He just said that his time is 1 a.m. now. He specialized in artificial intelligence, virtual reality, and AIoT. His research has significantly advanced AI-driven medical applications, agricultural precision analysis, and computer vision. As a senior member of IEEE, he also played a key role in the IEEE International Conference on Orange Technologies since 2015. Drs. Paul and Tsai will discuss the shift from old compression methods for images to advanced deep learning and show how these new techniques are driving innovations in healthcare and robotics and more. If you have any questions, please put that in the question Q&A session, and Dr. Paul will give a talk, and then Dr. Tsai will give a talk, and then we will answer your questions. The floor is yours, Dr. Paul.
Yeah. Thank you, Dr. Yu, for introducing me, and Dr. Tsai. Yeah, I'm glad to be here in this webinar, which is organized by the National Institute of Statistical Science and Canadian Statistical Science Institute. As we can see, the theme here is like MPEG-4 to deep learning, transforming audio visual analytics for healthcare and beyond. So I'm just going to take you back a little bit with this talk, and then we see and we move forward into the era that we are now, and we'll see various applications. So that's the agenda for today. Like I'll give you a brief history of MPEG, and then advanced video coding, the revolution of deep learning and its application to image and video analytics. We'll see various applications, some from my side and many from Dr. Tsai's side. So let's go back. So some of the challenges that we had in the early days for this audio video analysis or compression is that the storage and bandwidth. As we know that uncompressed video and audio data requires substantial storage capacity. And also, while we transmit these audio and video, there is always a limitations of network limitations like the bandwidth. And it leads to latency and even in most cases, the potential data loss that in fact impact the quality of the retrieved data. I mean, after decoding, the one that we see is not as that of the real one. Also, we had other limitations like real-time processing. We didn't have hardware that can power to handle some complex audio video data streaming efficiently. Again, they had the latency issue in that real-time processing. We had a delay. So we have to be, the response time is so critical when it comes to real-time streaming. Just imagine having a live broadcast in the TVs on 1970s and 80s. Yeah, they had a hard time at that time. Even if you go back, even 1950s, still we had a lot of issues. But manually, at times, things being, audiovisual data have been extracted. A lot of human effort was involved in those days. But as we move forward into 1990s, for example, MPEG-1 is like originally it was released in 1991 actually, and eventually they had a lot of parts they developed, part 1, part 2, and so on. But MPEG-1 is kind of a lossy compression of audio and video. So there's a lot of loss related to that. And again, then comes the MPEG-2. And again, MPEG-2 is used in digital video broadcastings and DVDs. They were started to use this MPEG-2. And they had, again, several subparts that can cover various aspects. For instance, even MPEG-1 subpart is like MP3. Maybe you heard of that. That was part of MPEG-1. Then we had MPEG-3, MPEG-4. Of course, MPEG-4 was very popular because multimedia applications, even sometimes it is somehow limited to certain devices and components, but via internet these days, when MPEG-4 came in, the video and audio was started to transmit or stream, you could say. So that's one of the impact of this MPEG-4. So this is one example of how audio video analysis has been done and how the data that have been compressed or encoded first and then transmitted via network, and it has been retrieved, and the retrieved place it has been decoded. We decode that. So this is the basic architecture of audio video coding format from MPEG-4. A lot of small things are involved in it. Let me explain some aspects that might be interesting. So for example, here we can see there is this temporal models. And temporal models are nothing but we can see there is a two frames are there. The one we call F1 and F2. And F1 is like a previous frame, and say F2 is the current frame. And we try to see the difference between these two frames. As you can see, there's a lot of redundancy, right? So a lot of places you can see it's gray, and very few places you see the motion. For example, the background desk and all the papers are just stationary. It's never moving. Probably the hand and the violin rod, that's the only thing moving, apart from the minor movement in those violin as well. So we try to capture this redundancy. That's one of the main part of the video coding. We try to capture the redundancy, and we try to capture the motion actually, the motion. So we call that as motion estimation and motion compensation. How do we compensate the motion? So from the previous frame to the current frame, when an object is moving, we try to follow this object and we try to find the same window. So for example, here we see this window here. We are looking for this the blue one in the next frame, and we try to find how much it has moved. So that movement we calculate, and that movement has been carried over or stored as a motion vector. And this motion vector is the one that we really need to, we need that information to rebuild or reconstruct the original image. So this is a simple technical aspect of that model that we had back then. And eventually after that, we had the advanced, the so-called advanced video coding, and H.264 architecture is given here. So as the video input comes in, we use, for example, the discrete cosine transform to transform the image, and then we quantize it. And as you can see, as we transform and quantize, there is certain losses happens, right? So yeah, we have to make sure the loss that has been lost because of this transformation and quantization is as less as possible. So again, in between, we consider inter and intra, two types of prediction, like intra prediction and inter prediction is like the motion estimation that we talked about between different frames. And we use the deblocking filter to compensate for certain losses as well. And for rebuilding, we need the inverse quantization and inverse transform for the image. So this is basically the architecture of H.264 that even now we use this standard, and it's kind of advanced standards, and H.265 is also there. And And why I'm giving these background is because this is how the video coding and video compression models were there until recently, we could say. And still, people are still working on different models. For example, multi-view cameras are there, and so multi-view coding is there. And that's another standard has been developed. So likewise, the International Telecommunication Union is developing different standards for all different types of video coding systems. And since 2012, there was a big shift, you would say, especially because of this paper when it was published, like the AlexNet was published, and AlexNet was published by one of the co-author of this paper is none other than Geoffrey Hinton. Geoffrey Hinton, he's the one who got the Nobel Prize for Physics last year. In fact, his student, Alex, is the first author for the paper, and they developed this model in which, in their architecture, they use CNN model, like a convolutional neural network architecture for image classification. They developed this for image classification, basically. And their performance was tested on something called ImageNet. And ImageNet is, again, originally that was established by a professor, I forgot the name. I don't know, I think it's Professor Lee, and she developed this kind of a huge database, and she ran a challenge or competition to check. And this AlexNet by far, like it stand alone. Like for example, in 2012, you can see this is the error rate is so low when compared to its competitors. So still, since then, AlexNet has been deployed and used in many applications. Basically, one of the features of AlexNet is that they utilized the graphical processing unit, the so-called GPU, for training purpose. And from there on, like everybody wanted to use GPUs. As you know, the GPU was trended, and NVIDIA and other companies, they started to make more efficient GPUs from there on. And we have a big turning point in audio video analytics. So there are a lot of applications have been used since then for audio video analytics. Even in medical, that has been used. So we'll see the application in a short time. Anyway, this is one of the landmark for the audio video analytics. So here's one of the work that I want to share. As we see these different types of models coming up, we analyzed the different models. Like we want to know, like convolutional neural networks is there, and then the transformers, they come up, right? There was something called transformers. We had transformers, and these two performance are quite good. So who is going to win the race for visual data? So we published this work in which we analyzed various approaches that's out there. Basically, those approaches that uses CNN model, like convolutional network. Like for example, AlexNet used that one, and there are a lot of other models. Like for example, ResNet is another famous one. Many people these days also use ResNet for their analysis. So they use CNN-based models, and there are a few models they are also using the transformers. It also came into picture. So here's an example of how CNN technique is used widely in recent years. This is from the Web of Science annual reports. And again, one of the features of the CNN for action recognition is to grab this data. Unlike the Gaussian estimations and intra prediction, we just go by block, and they convert these blocks into kind of a matrices form. And again, we take features of the images, and then we just focus on the features, rebuilding the features and identifying the features of any images. For example, if you talk about cat, and what are the features of the cat? Cat has 2 ears, 2 eyes. At times it has whiskers. I mean, they have a kind of a mustache, right? Yeah. So, and then it's kind of a fluffy, like they hairy and tail and cute, like those. Some of the features we train these features, And after training these features for the cat, and again, it has been trained for dog and several other animals likewise. And once you have a new animal fed as an input, this system, the model looks for the features. What are the features are there? And what is the probability that based on different features, is it a dog, is it a cat? It can identify. So that's how there's a change in the shift of how we try to recognize the images. But still, it doesn't mean that the entire video processing or compression technique is no longer valid. Still, we have a lot of other areas of research is still there. But when it comes to certain applications these days is well established. Results are there by using deep learning. And here are some examples of the publications in recent time using the transformers, vision transformers. Even in fact, the transformers, the so-called attention models are also used in NLP. Even today, people use that for building the large language models. And originally, the transformers were built for that purpose, and eventually people started to use it for image and video analysis. So here's one information we can look in for the transformers for action recognition. As we know, like in case of a CNN model, it just focuses on the features of any image, and then it trains based on the features. Unlike the features here, certain factorized self-attention is given. Attention is given to certain kind of token pairs. For example, as we see here, certain points were there, and those points are the points where we have to looking for more attention, you could say. It's kind of a self-attention for spatial and temporal things, like trying to capture the, for example, if consider this as a human, like if that is going to be a human, then it has to have 2 legs or 2 hands and a head and this kind of shapes, right? So if this is how we are going to train, then it's going to train based on various parts. It's going to pay attention to those parts. So since we focus on those attention, we are building a network that can give us positive or negative values based on that. For example, if you use a softmax, it can give you a result as positive or negative for agreeing to it that, okay, if it is positive, it means that the attention towards that part is positive. So we could conclude that, or we could rebuild that as a head. And then again, for the arm, you need 3 dots. If this is positive for 3 dots, then you have to build on. And eventually, if every attention is positive, then we can conclude that that is a human, for instance. So this is one example of how things been done. But when it comes to action recognition, there is a movement of hand, right? So for example, the arm is over here. You can see the 3 dots are here, and it's moving a little bit this way, and it's moving a little bit this way, and it's actually going up. So there is a movement in this 3 to 4 different, we could say in the past, we would be saying it as a frame, but in this case, it's not the frame. We just, we have put some attention to these models and paying attention to where the movement is happening, right? So since these dots are already in line for check, so we already checked the self-attention mechanism so that we can capture that action. So that's the difference between these 2 models actually. And we try to understand which model is better among these 2 models. So as we can see, when it comes to sparse connectivity or the latency between the actions and the output, as well as various other features, we found that there's a hybrid model. When you include CNN as well as transformer together as a hybrid model, that checks all the box actually. In other words, their performance is better than individual performance. So this is the, what do you call, the results from the question that we had in the past. Which runs the race in case of a visual data? Is it CNN or transformers? In fact, when we have advantage of both of that, it could give us a better results. So that's one of our work, and these are some of the examples of CNN model transformers and hybrid models that is out there. And you can see the accuracy of this hybrid model is quite good actually. And at times it is compatible to the transformers, but generally speaking, based on our results here, we found that this hybrid models would perform better if you could apply it. The next one is about another work that is published in PLOS ONE journal. So we use a deep sparse capsule network for non-invasive blood glucose level estimation. So here we use this so-called PPG. It's like a non-invasive optical technique that used to measure the blood volumes. And this is how the device architecture looks like. And it emits the light and it retracts this photodetectors. And based on that, it try to calculate the blood volume. It's kind of pulse. It just pulsates from the skin. From there, it actually calculates. So these days, this kind of research is getting popular because, so especially for those people who are diabetic, they don't want the needles to be pierced every day, right? So instead of that, they prefer a non-invasive or not piercing it, just having top of your skin. You try to understand. So for this, again, we build certain feature extraction models with the DSC net models, and then we try to classify, for example, those people with diabetic and non-diabetic. So at that end, we build this hardware actually. So this sensor board is placed, and then it's connected to the system, and PPG signal is sent to the convolution model, and then they are routed through this concatenated layers. And then these dense layers and concatenated layers are nothing but they are a group of deep neural network with convolutional neural networks. And then the output gives us the results, like it shows, okay, this person is normal, or this person is pre-diabetic, or this person is diabetic. So this is the two algorithms which were employed in this model. So these algorithms just gives us the information about number of layers used, the kernels, activation function is, ReLU activation function is used. And then, for example, the max pooling dropout rates. So this general algorithm for us. And then with the self-attention, as we know, the attention to certain features, you just focus on some of the features and pay attention to those features. It's kind of a little bit better model than that of the original model. So as you can look here, I didn't have the architecture, but just the algorithm. It's just this. It's kind of a CNN model because it has all the elements of CNN, including the flattening, dropout, and dense activation functions. So here's some differences you could see in the PPG signal for patients with diabetic, or in other words, with more sugar, and patient with less sugar. And the analysis simply initial stage, when you look at these things, it seems to be like almost same image. But as we observe closely, there are some differences in their signal strength. So that implies us to classify whether this person is diabetic or not. So we compared our model with different other models because we are not the only ones working on this non-invasive. There are a lot of people are working on it. And yeah, there are different models like BiLSTM have been used, decision trees, 1D CNN, XGBoost, and BBNN models are being used. And our model relatively performs better in some areas and not in all areas though. So we like to develop this better model into a next stage so that if it is really performing better, and also the size of the model that we have, the real hardware is a little bit bigger, we want to reduce the size as well. If that is possible, then it could be feasible for the patients to use. And one of the drawback of this analysis, like that, we had a very few patients. When I say very few patients, it's like in less than 100. patients were used, for our data. Okay, at last, I like to point out to this model. This is again healthcare model in the medical services, but this uses the federated learning system, which means it passes through the cloud, and collaborated machine learning techniques being employed with some joint predictive model. It's not just one model we have, like, okay, you try to predict whether there is a diabetic or not, or whether there is the COVID or not. Instead of that, it's kind of a collaborative model. It has all the different inputs from your healthcare personnel. E-health data set, it takes in all the information of a patient, and it's a kind of a semi-supervised. So you have supervised certain part, but some part is not supervised. So it's kind of a semi-supervised model. And this model shows us, again, this could be like used as a protocol type for medical emergencies, like for patients who are living in a old age home, for example. Their data has been collected and federated and given to the healthcare providers, the healthcare physicians or nurses who are monitoring their progress. And if there is any need, they can be alerted, and accordingly they can be respond to the needs. Again, for this purpose also, we use simple CNN model. The deep learning network has been applied over the cloud. These days, as you know, everything can be deployed over the cloud, right? So even though you do some certain things individually and deploy it individually, this system, we tried it to deploy it over the cloud, and this work is also published in IEEE Access. So this is some of the things that I want to share at this point. And I like to turn over to Dr. Tsai for more application. He has more application, actually, more application about this deep learning based system. Yes, Dr. Tsai.
Okay, so 1 second, let me share my screen.
I will stop sharing.
Okay, so hi, good morning. No, in Taiwan, it's actually like a very early in the morning, like 1:30 in Taiwan. So I'm here to present some of my research in artificial intelligence. And the first one is I want to introduce, like, I'm actually in Pingtung. Actually, my school is in Pingtung in the south part of Taiwan. Most people, maybe when you see Taiwan, maybe you heard like Taipei. Taipei is somewhat here. And this is Kaohsiung is somewhat here, like, but Pingtung is actually the south part of Taiwan. And there's some image for our school, and there's a YouTube. If you're interested, you can check later. And we should take this. So the famous of Pingtung is that we can see there's a mango. Mango is quite famous in Taiwan, and the other one is like a wax apple. And then the onion, I just did some of that. Is also very famous in Taiwan. So this is roughly a very brief introduction, and then I will go through with my recent research in image with artificial intelligence. So there are 4 topics here I'm going to share with you. So the first one is a drug pill detection, because in Taiwan sometimes we have unwanted medicine. So for this kind of unwanted medicine is and maybe it's out of date, maybe you didn't finish it at all, so you just give it back to the hospital. So when it comes to hospital, so hospital need to assign some extra people to do the classification. It also increase their work. So how do we do with that? How do we do that is we just use kind of a CNN model and to do something like for this kind of a PO classification. So what we do here is there will be like a 2-part. So you have to first one for doing the PO localization, and after that you do classification. So this is a result. Like you can see, there's a numbers. The numbers represent their category. So different kind of a number represent different kind of a category. We can see something here. And what we do is mainly there are two networks here. The first one is you have to localize your appeal first. And in here, we can use something like a ResNet 50. And the other one is once you localize the appeal, right, then you have to classify what is the appeal, then give to identify what is that, then give the answer. So we can see somewhat like this. This is all data set what we collect. Actually, this is covered with one hospital in here. So we can see that totally we have 612 classes for the medicine, for different kind of medicine. And totally for our training image, we have around 2.3 million. And for validation images, like 34,000. And for testing is like 1100. Then we can see by using different kind of model, and this is the result. The left-hand side is our proposed one, and this is a comparison with a different kind of a method here. So you can see ours, we can localize like more peers here. And then this is a result, like we can see that they're showing some numbers here, which represent the different kind of a category of those kind of medicine here. So for this topic, actually, here is something we can see for like a type A. We can see like figure A. Figure A is actually they are all this kind of peers. They are all from the same company. So in the one side there's one mark, and the other side they have different kind of number, right? And also their shape is all like a round shape. So if this kind of peer layer fall in this side, actually we cannot detect like the other side. So you may have some kind of a like a false positive, something like that. And this is the other case. They are too similar. There's no feature or imprint like you can see. So it is also make your accuracy decrease. And this is for first topic, and we have published in the IET computer region. And the other one, this research during previously, because we know COVID affect us quite a lot. And during that moment in here in Taiwan, we all need to put on a mask. So if you put on a mask, is it possible still you do the face identification? In the moment we are doing this, like for this one, you can identify like where is your eye, your nose, your mouth. But what if you put on a mask? How can I know like this is me or this is someone like that? So this is the one we are thinking in that moment. And in here we are using some kind of a like a single stage headless. So in here we actually use VGG16 because the parameter for VGG16 is less. So we are using in this application. And so this is like our system architecture. We do do face detector first and find the ROI of your face and find the place of your face, and we do alignment. Then we use some deep neural network and to do feature extraction and find like who are you, someone like this. So here mainly we are using a single stage headless, and because we want this kind of application should be work in real time. And for different kind of branch, they can handle with different kind of faces, like this one, the M3 for big face and M1 for small face here. And here is the data set what we collected and what we defined. For example, like if you show your eyes, even you put on your glass, if you show your eyes and your nose, we say this is 25% accorded. And if you put like glasses and mark we cannot see your eyes, so this is also like a 25% coded because you show your mouse here. And but for this, if you mark your nose and your mouth, and we say this is 50%, and for this one is a 75%, and with a different kind of a pitch angle and yaw angle also. So this is a roughly our data set. And then we come to the experimental result. We can see if there is a 50% occlusion still for 1 meter, we accuracy, we can still reach like a 95%. Okay, and with we can check this row with 50% occluded and the proposed system with a certain ID, or we are trying to with some different kind of data set, we can all reach like 80%. This result is again published in IEEE Access. This is another one for a something like a detection, and you may think this one is a bit strange. We are detecting larvae here. So what is the use of this kind of a larvae? Actually, we can see this kind of a insect is called a black soldier fly. So why we are doing this is because in Taiwan we have a lot of unwanted food. So what do you do with this kind of unwanted food? Then there is actually not only in Taiwan, in many other places in the world, they are using this kind of a small larvae to process those kind of unwanted food. As long as it is organic, it can be digest. This kind of a larvae, they can help to digest, help it to turn this kind of unwanted food to become like a fertilizer, that kind of stuff. And by detecting that, we can see actually for this kind of a larvae, they have a different kind of stages from egg and to pupil. So they have from here to here, they will pass through like a stage 1, 2, 3 to till like a pupil stage. So we need to know during like a stage 2, 3, 4, like this 3 stage, they eat a lot. But if it goes to like stage 5 or like 6, in that moment they eat very less, or we can say like they are going to turn into pupil, so they do not eat. So in that moment we should not eat too much, because if you eat too much, they cannot like eat that much. So those kind of food they will tend to like cause more too many ammonia. So and that is not good for the other stages. So we need to control like how many quantity of food we should add. So then we need to calculate like how many, the amount of lamb, and during your, usually they are using the pool, very big pool to raise them. So we need to like estimate how many of them they are inside the pool. And here we are using YOLO, those kind of architecture to detect like the lava. So you can see the larvae, actually they are very small. This is a scalar here. For the stage 1 is less than, is around like a 0.3 centimeter. And for the stage 6 is around like a 2 point something meter, or so centimeters. And here we also changed something inside the YOLO 11, and like we changed some kind of originally they use the CNN, but we found we want it to be the size to be smaller, so we changed something about with some model inside. And also we built one server for that, because we wanted to use in with your cell phone, so we can take photo from your farm, and you can directly take the photo for your larvae and send to the server. Like this is the service running behind, and once you recognize the result and you send back to the cell phone and to show like the amount of land, like how many stages roughly, because you have to enter some information about your pool, like the size and the depth also. Then we can calculate the estimate, something like that. So this is the UI interface, and you can like import photo directly from your camera, and you can also and upload the photo in your from your image. And this is some of the result. Here we compare with some other YOLOs, because we know YOLO we have a different kind of a version here, but this is our proposal. We basically based on YOLO 11X, so we can compare here. In comparison with the YOLO 11, we didn't our performance is even better, a little bit slightly better, but our model size is smaller. Or that is because we changed some of the architecture inside YOLO, and also our parameter is smaller. And yeah, by comparison with different kind of models, you can see like this is YOLO 11, this one is YOLO 11, this is our proposed, and you may see like this RT dirt, their detection result should be seems like more, right? But actually they have many false positive, and if you have too many wrong detection, actually affect your overall accuracy. This one is already submitted and it's under review. So this is our recent work. And the other one is something like related to generative artificial intelligence. So the previous three is more focused on object detection. You can see we are detecting PO, we are detecting face, and we are detecting larvae. And this one is a little bit different. Like we have a cooperation with a dermatologist. So what we do here, this is a human face, and mostly in Taiwan, there's some girls, we can say that if it comes to some age, they have a melasma. So if there is a melasma, they must find some center, some beauty center, they can help you to deal with your melasma by using laser or some kind of method. So they in the hospital they do have like this kind of machine. They can take some photo, and this kind of photo they can generate some kind of melasma image and a hemoglobin image. And the motivation is the doctor feel like this kind of machine is quite expensive. They feel if you can use cell phone to detect melasma, and we can just put that kind of as a record, and we try to reduce the medical dispute, because some people argue like after treatment, like I don't see my face is melasma is getting less or something like that. So the doctor also want to protect themselves, so they need to create something like take photo. We say that like before treatment and after treatment, we need to let you know, hey, what's the difference between that? So what we do here is we use a model called pixel to pixel HD, and this is actually a generative model. In generative model, we do need to handle with discriminator and the generator by generate those kind of image. And once we generate those kind of image, we use another module for melasma analysis. So in here we can see the output. Actually, we have a melanin image, we have a hemoglobin image, and we also have a combination of that. And this one is normally from the doctor's information, like our melasma will normally show up in your side of your face. Like this is left hand side, right hand side, in the middle, you can see that. In most of the area, most of this area, you can see melasma. So we need to take some angle of those kind of photos, and this is the result. Actually, this is a combination of this is a melasma image, and this is marked like by using this kind of a process. We mark it this kind of a, like you can see the darker color, and we mark it, and those kind of feature, those kind of image will be generated, and for dermatologists, they can explain to patients and to say, are these melasma or what? So okay, this is corresponding to real image. You can see something there. Their skin is a little bit darker here. So this is the data set. Why we are using pixel to pixel HD, and why this is suitable to use like a discriminator, generator, those kind of a generative model is our data set. Those kind of data set actually come from the hospital also, because those kind of data set is paired. This is the like a original image, and this is a hemoglobin and the melasma and the polarized image. So by doing this, collecting those kind of data set because it's paired, then so we can use a generative model. And this is a result. Like this one, the image A, this is the data set, and the image B is generated. We can see it's a little bit hard to see the difference by using your human's eye. So this is from pixel to pixel HD. And of course, we try some other method also. The cycle gain is also famous in the moment. So we also try cycle gain. And this is a previous version of the pixel to pixel. We can see that. And this is another one. This image is a hemoglobin. For every time, actually, we need to generate two kinds of image. One is like a melasma, the other one is a hemoglobin, and we also have a comparison with pixel to pixel HD, somewhat like that. And we can see like pixel to pixel HD is very close to the original data set. And this result is published in Algebra Access last year. Okay, I think this is my very quickly to introduce my work. So can we have a like a short comment or something?
Thank you, Dr. Tsai and Dr. Paul, for your wonderful talk. Our attendees, if you have any questions, please put that in the Q&A session. I will start with a question for both of you. When do you think, I saw a few applications of this AI image analysis used in the healthcare. When do you think that, and how can we justify that AI can replace the human diagnosis? I mean, the human physician diagnosis. Will there be a rule that for the accuracy or anything?
Yes, I think right now, still, for example, some decision like are done with assistance of AI. For example, in AI radiology, people use AIs a lot. And even like I heard about diabetic renotherapy or screening purpose, they use AI, but still it has been supervised AI, like physician has to supervise the system. And the anatomy, or you can say, of humans are quite complex. So it's very hard for us to make it fully autonomous. It's not like just like a autonomous car. Like even today, we don't have a fully autonomous car. We still have self-driving cars are limited to some extent. We don't have full autonomy. So I feel we have to wait for a long run, because it's not only about ethical issues or insurance issues, insurance claims and things like that. The AI has to adapt, but also the productivity, like the outcome, is also needed. But of course, these days, some places where robots are used for surgeries. Yeah, so for certain things they can do. And I think in the future, for certain things, also like self-analysis or some tools will be there for humans to analyze themselves. Or there may be another area of new outcome will come where we can actually check most of the treatments, or we can actually consult a physician, like a kind of a digital twin, you can say, of our body. Our body's digital twin will be there, and that twin you can actually monitor its growth based on our activity. But this is still a long run, a long shot, I could say. And as we know, like general intelligence, the artificial general intelligence is still a long way to go. So what I predict or what I expect is like there are many areas of research is still going on, but for healthcare, a lot of investment is also going on. But it's nothing like if you really expect to have a fully autonomous physician who could care for a human, then it's going to be maybe in 2050 and beyond, I think.
Thank you. And another question I'm having is that as you use AI to fit the model because of the super computing capacity as the technology develops, you can easily overfit a model. But sometimes if you don't go to the specific decimal, you can make a very big mistake in diagnosis. So how can you balance the overfit of model and accuracy of the model? How will
So I think
do
that that has to do with the domain in which you're working. I mean, the domain of a place where it is employed. Like for some medical treatments or medical like for example, if you want to identify certain cancer cells or things like that, it's kind of a very critical things, and you cannot have even like 0.001% error. Cannot, like for example, like if you have like if there's like millions of cells and if you're missing one, that's like 0.0001, like, so you can't have that error. So it is domain defined. On that aspect, you have to scrutinize. You may have several layers of different models so that you don't really overfit the model, because generally speaking, as you said, if you want to cover everything, then you definitely it will overfit, and practically speaking, it can't have it's impossible for us to work that way. But yeah, this is one of the biggest challenge, I could say, that medical sector is facing, and sometimes this has been ignored also. So we should be careful as we develop drugs or as we develop many AI assisted models. We should be very careful about negligence of that aspect, because as we know, the binary model is kind of discrete, and it's not a continuous one, but the real model, everything is continuous one. And even if when you want to have certain assignments in a variable, for example, if you have a variable and a variable assigned as an integer or say for example a float, that can be a big difference actually in holding the particular value. So yeah, that a bit of caution is needed on a different aspect of those who develop any models which could assist physicians.
Are those all the limitations of using AI for healthcare? Is any other limitations that you want to emphasize?
Maybe I can answer that. And for us, the hard part should be the data. Actually, maybe we know how to try to run a model or try to run different kind of method, but actually we have nothing in our hand. For example, like if you're the doctor or you are the nurse or you are some kind of a medical service, some kind of area, but if you don't give us the correct data set or correct image, for example, like actually when collecting the pure like kind of image, if they don't release, it's impossible for us to get those kind of data like that. So if the doctor or like a dermatologist, they don't provide any information, there is nothing we can do, because what we can do is only we can find like a public data set. But some kind of a we can say like a special disease, or for example like you want to detect some kind of a lung cancer, right? When we see those kind of a image, we actually know nothing. When you see like kind of a CT or that kind of image, we need some assist from the doctor. They need to mark that which part is some problem. So there is we need to do labeling. So correct labeling is very important. So if it is like a 10,000 or like 100,000 image, it is a lot of work, and we need to make sure like everything we label is correct. It will only helpful to train your model. If we find like a 50%, then of course your performance will not be okay. And that is like our hardest part there. So we also try to find some cooperation to try to find some requests that if if you think like, oh, this might be like a computer can help, then maybe we can work on that. Okay.
Thank you. And thank you again for joining our webinar that is supported by the National Institute for Statistical Science and the Canadian Statistical Science Institute for their, we also thank them for the sponsorship. And thank you again for attending this webinar, and we will see you maybe in next month, maybe. And I will adjourn the webinar.
Thank you.
Thank you.
Tsai.
Thanks.
Yeah.
Okay, thank you. So